Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of organic chemistry lectures and solutions to homework problems. In this Scribblecast lecture, we're going to be doing samples of elimination reaction problems. Having covered the E1 and E2 reaction mechanisms, we're going to be looking at how alkyl halides undergo elimination reactions. Now, the first point to make clear is that of the two mechanisms, it is the E2 reaction mechanism which is important for alkyl halides. Typically, alkyl halides do not react via the E1 reaction mechanism. Also, whenever the E2 mechanism cannot occur, substitution will occur as the alternative route if possible. Now, we're going to indicate, in the simplest sense, we're going to indicate, if I say take isopropyl bromide, or why not, let's go with, rather than isopropyl bromide, let's go with sec-butyl bromide. We're going to indicate elimination as being the major pathway by supplying heat to the reaction. So if I supply, for example, a base such as sodium hydroxide, you know the base or nucleophile in the reaction is the OH minus. A nucleophile is attracted to positive charge. A base is attracted to a positive charge on H. Nucleophile positive charge on carbon. You know that it's the negatively charged hydroxide that is your base or nucleophile, not the positively charged sodium. If you see a triangle under the arrow, the triangle means the reaction is occurring with sufficient heat so as to cause elimination to be major, if elimination can occur. If I wanted E1 in an alkyl halide, I will actually have to write E1 under the arrow. Okay? If I write E1 under the arrow, you will go by the E1 mechanism. However, if there is no E1, you will assume that it is E2, and you must follow the rules for E2 elimination. In this case, E2, which requires antiperiplanar elimination, because I have not restricted the chirality, I have not shown the three-dimensional structure, and there's no ring structure to hinder conformational change, I may assume that the methyls and the ethyl groups are free to rotate and undergo conformational change so as to get H's anti to the bromine. Now, what I must look for are beta hydrogens. You see, the carbon bearing the bromine is referred to as the alpha carbon. Carbons attached to the alpha carbon are referred to as beta carbon. Beyond that, we have gamma and delta carbons. Now, the beta carbons hold what are called the beta hydrogens. In order to build a double bond, the bromine must leave, and a group must leave from the other atom to which the double bond is forming. In other words, we must lose an H and a Br. That's why elimination is often, of alkyl halides, called dehydrohalogenation. All right? Now the point is, I can pull an H off any of the beta carbons as long as they can get anti to the bromine. So removal of beta hydrogens is prerequisite to forming the double bond. The hydroxide will come in, pull an H off, and I can draw the possible products. So if I pull an H off the beta CH3, I will get this molecule. And if I pull an H off the beta CH2, I will form this molecule. So two different products are formed. 1-butene and 2-butene. I also can indicate who is major and minor. In most cases, the more stable double bond will be major. There will be one exception to that, which we will examine. When the more stable double bond is major, when the more stable double bond is major, it is referred to as Sayseff, sometimes spelled with a T, sometimes without a T. Sayseff elimination. I'll just put N for that. Superscript N is a short form for elimination that I will often use. If the less stable double bond is major, less stable double bond is major. This is referred to as Hoffmann elimination. Hoffmann elimination. Now, Hoffmann elimination typically does not occur. It's a rarer type of elimination. It has to be caused by some extraneous factors. We're going to look at the end of this lecture, or scribblecast, at one example of Hoffmann elimination that you need to know. All of the eliminations we're pretty much going to be looking at are Sayseff eliminations, which means you have to be able to identify the more stable double bond. So of the two double bonded molecules I've created, one could ask which one is more stable. If you remember to the end of the last E2 reaction mechanism, and when looking at the E1 mechanism scribblecast, we examined what is the most stable type of double bond. And I'm not sure if we did it in the E1. We may have. I think we have. The more stable double bond is the double bond that has the most carbon substituents off of it. This is determined by heats of hydrogenation. We'll examine that in the alkene section of the course. If I isolate the double bonds here, if I take, for example, let's say a red, and I draw a circle around the double bonds, and I say who has the most carbons off of him? I see in the top molecule, 1-butene, there's one ethyl group, one substituent. Off of the 2-butene, there are two methyls. There are two substituents. More substituents of the double bond mean more stable. And so 2-butene, since we're doing Sayseff elimination, since the more stable predominates, would be indicated as major. And the 1-butene would be indicated as minor. Now, there will be occasions where you will have to indicate whether or not elimination can actually occur because of the restriction of antiperiplanar elimination. In this case, we assumed anti-elimination could occur because of conformational change available to the molecule. But in some cases, you may actually have to draw and look at the product. Let's try another example, and let's see what we can draw in this molecule. Now you may, for example, get something like this. Where you'll be given certain groups that aromatic ring, and then H. Where, for example, and the molecule is actually drawn in a eclipse state here. This is where your colored ethane, and I'm going to put some dots for the carbons so you can see where the carbons are in the rings. Let's fix that one up. So we've got a couple aromatic rings here. Now we might hit this with a powerful base, such as sodium. Maybe this time we'll use ethoxide. What solvent would you use for sodium ethoxide? If sodium ethoxide was dissolved in water, the base would deprotonate water, make hydroxide, and hydroxide would be a base. If you wanted sodium ethoxide to be your powerful base, you would have to dissolve it in ethanol. Why would you have to dissolve it in ethanol? What if the O minus CH2CH3 deprotonates ethanol? What do you get? You get this exact same thing. You get O minus CH2CH3. So this typically is our solvent. Use the conjugate acid of the base. So sometimes you'll draw solvents in there. We'll give it a triangle to indicate elimination. Again, remember, triangle means just enough heat to cause the elimination. Some cases, elimination requires a lot of heat, hundreds of degrees Celsius. And sometimes the elimination occurs really easy. In this case, it would occur very extremely easy. Would not need much heat above room temperature at all. Well, the problem with this reaction is we don't have the molecule in an anti-configuration. The Br and the H are not antiperiplanar. Let's begin by finding our alpha carbon. The alpha carbon's located here, so the bromine's going to leave. I've got to pull an H off a beta, so this H right here can't leave. That would be pulling the two atoms off one carbon. It won't help you make a double bond. Beta carbon is located here, but this beta carbon has no hydrogen. There are 3 bonds. If you can't see that because of the circle, let me draw some pi bonds for you. There's 1. There's 2. There's number 3. This carbon right here has 1, 2, 3 carbon bonds, 4 carbon bonds. There's no H off of that. So that certainly can't be used to make a multiple bond. The next beta carbon's over here. And there is an H on this beta carbon that we could use. And this H certainly can be removed, but it must be anti to the bromine. Now, I can rotate this. All right? I can take this molecule and rotate it until a conformational change, until the bromine swings into a position. If I do that, the bromine will swing to a position this way, where it's straight up and down. The H will be swing up, so it's wedged towards me up. And this will be, the phenyl group here will be dashed. Let me draw that for you. So I'm just rotating this molecule. I'm going to try and get it into a conformational change. So I'm not changing this carbon at all. Probably going to have a hard time drawing my aromatic ring small enough to stay on the screen. That's just terrible. I'm going to have to move this over a little bit. Try raising it a bit. Actually, why don't I draw the ring first? Okay, maybe that'll work. Dots for my carbons. And make a wedge. There's my C. My CH3. And my H. Attached to that will be a carbon. Strut straight across. And the wedge up will be an H. Make that a dash. And the other aromatic ring and the wedge will hold the H, and now bromine. Okay, now remember the dash is going away from you. The wedges are coming out at you. When we pull this H and this BR, we are getting anti-elimination. The antiperiplanar elimination has a consequence when you have two chiral centers like this. If I look at this molecule and I prioritize, say at the beta carbon here, so we prioritize here first. The carbon with the bromine's number 1, the carbon with the aromatic rings number 2, 1, 2, and then the methyls number 3, 1, 2, 3. That'll create a carbon that is S. On the alpha carbon, bromine's number 1. The aromatic carbon has carbon, 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 3 carbons. This has 2 carbons and an H. So the aromatic carbon's number 2. So bromine's 2, bromine's 1, phenyl's 2, and this big carbon, this S carbon, this beta carbon is 3. 1, 2, 3. This will be R if you project the hydrogen to the rear. Now, you didn't have to do that to solve this problem. You had to just be able to draw the anti-species. In fact, you didn't have to draw this on the solution. You draw it on scrap paper. Since you're allowed to bring a colored ethane into a test with you, you can use your colored ethane to do this by labeling the colors to certain functional groups. When the bromine and the H leave, the H here and the phenyl both get wedges. So they appear on the same side. Okay, and so the H and that phenyl appear on the same side. The methyl and the other phenyl appear on the other side. Together. The antiperiplanar elimination leads to E2 being stereospecific, Because it's stereospecific, you get a specific stereoisomer forming here. In this case, the SR molecule gave us highest priority on this side, 1, 2. Highest priority on the other side, 1, 2. And 1 or 2 on opposite sides, so this is E. This isomer is E. Okay. The E isomer forms. Would it always be E? Will SR always be E? Well, let's go to a different color. What if instead of this H, we had a fluorine where the H was? So this H here became a fluorine, so that this H was a fluorine. When we prioritize in that case, the phenyl would still be higher priority than the methyl. But fluorine is high atomic number than carbon, so fluorine would have been number 1, 2. Fluorine's a bad leaving group, and so fluorine probably would not leave during this reaction. So given these two values, both high priority groups on the same side, when it's fluorine, you would have gotten Z, a Z isomer. The reaction still is stereospecific, producing only one stereoisomer. But don't think SR always means you must have E. All right? It's important that you understand what the actual designation of the stereochemistry is depends on the prioritization of the groups off the double bond. So antiperiplanar elimination in the E2 case leads to a stereospecific reaction, producing one stereoisomer. In fact, if for some reason the molecule can't get anti, then the elimination will not occur. Let's take an example of that, or take a look at an example of that situation. Suppose I have a chair conformer and I have a bromine in this position. Well, let's begin by asking who is anti to the bromine. So I'm going to redraw this molecule, and I'm going to show, so I'm going to draw it again. And this time I'm going to use a different color for the bond to bromine. So there's my carbon-bromine bond. And I have to ask which bonds are anti to that. Which bonds move in the opposite direction perpendicular to that? Well, it is in fact these two bonds. Where are the beta carbons? Well, this carbon is beta to the carbon that has the bromine, and this carbon is beta to the carbon that has the bromine. This is my alpha carbon. The carbon that bears bromine is the alpha carbon. To get anti-elimination, I must, antiperiplanar elimination, anti to the bromine must be a hydrogen. But what is it at the end of these red bonds that are anti to the bromine? What's that dot and that dot? Those are carbons. You can't pull carbons off. You can't pull carbons off. I'll make blue dots for all my carbons so they're easy to see. So while in this conformation, no elimination can occur. Does substitution happen? Not at all. Remember, at room temperature, with chair conformers, you can get a ring flip occurring. So at room temperature, this molecule can undergo a ring flip. So let's draw the ring flip structure. I can do that. If I draw the ring flip structure, now my bromine bond is down. Off of the beta carbons, the anti-bonds are in this position. Okay. So put dots for my carbons so they look clear. So we have bromine here. We have an H equatorial. We have an H equatorial and an H equatorial. We also have our axial H's. So if I look at this, the bromine when it's ring flipped is an H off the beta carbon. You can pull either of those H's off. So if I were to draw my product, I could draw it where the bromine leaves and an H leaves, and a double bond forms. Double bond forms between time drawing this. There. And you end up with an H off here. And an H off here. Now, you say, well, can't the double bond form on the other side? Well, let me ask you, is this carbon chiral? To be chiral, we must have four different groups. We have a bromine and an H. We have a CH2, CH2 here, CH2, CH2, and it's tied up to this pointy end here, the CH2. It's identical all the way back. Because it's identical all the way back, these two groups are identical. This center's not chiral. Hence, if you make the double bond here, or you make the double bond back here, makes no difference. It's the same molecule. So ring flipping allows you to get the bromine anti to H's. Because it can get anti, and then the product can ring flip, I could have drawn it this way, and it certainly would be the same thing. Put the double bond there. I'll put dots for my carbons. There. And so cyclohexene's chair conformer is formed. So even though the bromine couldn't leave from this conformation, the final product could ring flip back to the conformation that originally was there. So a ring flip gets you anti, it eliminates the HBr, producing a double bond. Either position produces the same molecule, so you can represent the product as this. Well, let's look at another chair conformer situation. And let's draw a chair a little larger so we have a little more room. So here's my bromine. I'm going to put it axial so we don't have to ring flip it this time. And down here I'm going to put a methyl. Hard to see. Here I have an H. Now, in this chair conformation, we see that the bromine is axial. And we check what's anti on the beta carbons. So if I look over here, put dots for my carbons on the ring. So you can see them better. Off my beta carbons, anti to this bromine is a methyl. Can you pull methyl off to make a double bond? No. When the bromine leaves, the group that's anti must be a hydrogen. No double bond can form here. What about here, on this beta carbon? On this beta carbon, we have an H. On this beta carbon, we have an H. Okay, I can pull this H off. When I pull this H off, if I'm given a base and the symbol for elimination, which is heat, I will get the double bond forming here. And the CH3 will still be down on the other side. Okay? Because it's chiral, producing a double bond on the other side would have produced a different product. And so, since you can't pull off the CH3, since you can't get this H anti to the bromine, this is the only alkene that forms. What if we change this a bit? What if I had a CH3 here? H, and H, CH2, CH3, and my BR equatorial. Well, this is a situation now where we have to draw the ring flip of the starting material, and you do that on scrap paper to see if you can get anything anti. The reason you have to draw the ring flip is which bonds are anti to the bromine? Well, let us draw them in red. Here's my bromine bond. What bond is anti to that? It's those two bonds. They're anti. And because those two bonds are anti from the beta carbon, they end at these carbons, we can't pull carbons off. So while the bromine is equatorial, it can't leave. You have to have a ring flip. So we can draw the ring flip. That's not a problem. I ring flip. There we go. Here's my ring flip. The bromine, what was equatorial, now becomes axial. And what was axial becomes equatorial. So the methyl is now axial. The ethyl is now axial. Who is anti? Who is anti to this bromine? Well, what is anti to this bromine is the methyl and an ethyl off the beta. Let's find our beta and alpha carbons. The alpha carbon is the carbon with the bromine, so it's there. My beta carbons are the ones next door. And anti to the bromine, extending up, while the bromine extends down, is the methyl and the ethyls. You can't pull off a methyl and ethyl. So in this case, E2 elimination is completely blocked. And so even though you have heat, no elimination will take place. Now you go back to your substitution rules and you say, well, if elimination can't happen, what is the substitution pathway? I look at my alkyl halide and I say it is a secondary alkyl halide. Secondaries can go SN1 or SN2. With a strong nucleophile like hydroxide, SN2 is favored, and so I'm going to get backside attack on this molecule. What will happen is the hydroxide will come in from behind, and the bromine will leave. The H will invert. The center is chiral, so we have to show inversion. So I draw it. The H inverts, and the nucleophile OH is on. I have my CH3 here. I have my CH2CH3. Very good. With my H's down, try and draw this more accurately. There we go. And there you have it. A substitution product because anti-elimination was not possible. Now, I will admit, in rare instances, you can get strange effects that would make this secondary 2-sterically hindered for the SN2 to occur, but this would be a special case, and we're not looking at that. We'll examine these types of cases in second semester. Okay. Let's try another chair conformation. What if I drew this? Let's give us a little more room. And what if I had my BR here? And say I had, I don't know, anti-CH3 here. Let's put a CH3 out here. And, why not a CH3 here? Of two CH3s. So the molecule's no longer chiral. The chirality is lost. And we hit this with a powerful base like methoxide. And again, if I was using methoxide, I'd make sure I use methanol as solvent to dissolve the base in. And apply heat. And I come along and I quickly analyze this and I say, the bromine is straight up. An anti-bromine is a methyl and another methyl. And since you can't pull methyls off, elimination is not possible. And so I come along and say we must get substitution. And so I say backside attack, SN2. But wait a second. Why SN2? Well, it's a strong nucleophile. But you forgot to ask what kind of alkyl halide. Okay, look at the alkyl halide. The carbon with the bromine has 3 carbons attached to it, so it's tertiary. Can tertiaries go SN2? No. So even though it's a strong nucleophile, it would go SN1. What would SN1 do to a chiral center? Well, SN1 to a chiral center would produce a racemate. But this center's not chiral. So when the bromine leaves, if and when the bromine left, I would not have to show racemization because there's no chirality. Because there's no chirality, I could just put on the OCH3 as a nucleophile in any position. So drawing it this way, or drawing it a curved bond, drawing it this way would be the same thing. Or would it? For simplicity's sake, because we've lost our chirality, we would hold it to being the same thing. In actual fact, it would begin to look like we are getting, if I flatten this all out, CH3 up, 3 down, they would be structurally different due to geometric isomerism. Because these centers, here and here, are chiral. Not a nice example at all. So you'd actually have to show this. Although this center is not chiral, there is a difference in the structures. And I'd have to draw both. Well, even if I saw that, I wouldn't have to worry about it. You know why? Because substitution does not occur here. What? Substitution doesn't occur here? This would be wrong, even if you drew both. Why is it wrong? Why is that wrong? Well, it's wrong because we missed an antihydrogen. What? Let's go back to the beginning. We stated that bromine is our alpha carbon. Bromine's attached to the carbon that's alpha, and we have to look for beta carbons. We found that there was a methyl anti the bromine at that beta carbon. At this beta carbon, we had another methyl that was anti. And then, right here, there's another beta carbon. And this beta carbon's not restricted by the ring, so he is free to rotate. Because he's free to rotate, the methyl hydrogens can get anti. And so these structures need not be drawn. And the complication of racemic addition by attacking a chiral center need not be considered in this chair conformer. So the complication that the center was achiral, but the other centers weren't achiral, didn't enter into the question. So, remove one complication by realizing we missed an antihydrogen. And that's easy to do. So what antihydrogen did I miss? Well, you missed the one on the methyl. And so when this elimination actually occurs, you would get a double bond out here to the CH2. To the CH2. Okay. Put our methyls back in. This would be the product that would form one alkene and only one alkene. Let's try another scenario. What happens if I very easily show the possibility of three different products? OH minus, heat, E2 elimination, find your alpha carbon and your beta carbons. The alpha is the carbon with the bromine. So this is a beta, this is a beta, here's a beta. All of the beta carbons have potentially antihydrogens. That means during elimination, I will get potentially three products where double bonds form, and they are different molecules. If the beta carbon with the CH3, if the anti-H leaves with the Br, I'll get the double bond forming here. My CH3 here. My other CH3 there. If I pull the H off the beta carbon of the ring that has the two H's, try to make them parallel. get the double bond there. And lastly, if I pull the H off the beta carbon, that is the methyl, off of the ring, I will get that. So I get that plus that. And because there's 3 different products, I have to be worried about Sayseff elimination and identify who is the major and minor product. In this case, if I look at the double bond, this carbon and this carbon of the double bond has 1, 2, 3, 4 carbons off the double bond. This carbon and this carbon of the double bond have 1, 2, 3 carbons. And this carbon and this carbon have only 1, 2 carbons. The one with the most carbons, most substituents, is most stable, and when the most stable is major, you have Sayseff elimination. That guy would be major. This one would be minor if Sayseff elimination is followed. And we will assume it is followed unless you're given a specific exception. I'd like to go back to that one. Try to make a scenario where substitution couldn't happen. Remember, if you asked to do E1, let's try that in this case. That's what we'll do. Let's try a problem where you're asked to do E1. Now, I know alkyl halides go E2. But occasionally on a test, to test you on E1, I may draw an alkyl halide like this and force you to make it go E1. So I might say draw something like this. And just to see if you're awake and paying attention, give it a weak base, because E1's favored more by weak bases. Triangle, meaning heat, and I will have to write under the arrow E1. If I write E1, you must apply E1 rules. That means you can't say, oh, the double bond won't form here because there's a methyl anti to the bromine. Antiperiplanar elimination is restricted to E2. So if I put E1 under the arrow, you must follow E1 rules. And what's that? Well, you form a carbocation. So draw your carbocation. Whenever you have E1 or SN1, you always draw the carbocation on scrap paper. Okay? And if the bromine leaves, I would get a carbocation that's trigonoplanar. I draw it here. And I have to ask, what kind of carbocation is that? Well, indeed, it is a secondary. There are 2 carbons, one here, attached to the carbon that bears the positive charge. So the carbon bearing the positive charge is secondary. Is there anything I can shift? Well, I can do a 1,2H shift. If I do a 1,2 hydrogen shift that hydrogen over, I will get this and this. And the H will shift to here. My CH3 will still be here, and I'll have a plus. Now this carbocation is tertiary. So it's a more stable carbocation, and as such, it will form. What's interesting is look at the original molecule. If the double bond had formed here, there'd be two different double bonds. I could have pulled an H off on this side because this center is chiral. These two centers are different. When the alkene forms here, you'd have a 1-methylcyclohexene or a 3-methylcyclohexene. Two different products. But once it shifts, no matter where I pull my H off of, which beta hydrogen, I would form the double bond here or here. It's the same thing. Because these two groups all the way around the ring are no longer chiral. And there's only one center. So in this case, you've lost chirality because of the 1,2 hydrogen shift. So if, for example, I draw both possible alkenes, try to draw them, whether I draw it like this or I drew it like this, these two are the same. And you can tell that by simply naming it. They are both 1-methylcyclohexene or 1-methylcyclohexonene. The point is they're identical. You can ring flip and flip the whole molecule over and you'd find them the same. However, the 1,2 shift does give you the opportunity of making a different alkene. So although these two are the same, so I only have to draw one of them, there is another alkene I could draw that is different. See, you have to still find the beta hydrogens even if you're doing just E1. And the reason for that is once you've done the shift, the beta positions determine where the H's can come off. And beta is next door to the carbon bearing the positive charge, the carbon where you're originally going to form the double bond in the first group left. Because of 1,2H shift, that position is shifted to this position. So that's your alpha position. That means this carbon's now beta, this carbon's now beta, and this carbon is now beta. Well, while these two H's make the same alkene, if I pull an H off the CH3 and put a double bond here, that's a very different alkene. And so, in this molecular case, two products would be possible. And once again, I could indicate major minor. Find the carbons of the double bond. In this case, the carbons of the double bond have a carbon here, and a carbon here attached to them. That's 3. This double bond has a carbon here and a carbon here attached to the double bond. That's 2. More substituted is better, more major when you're doing Sayseff elimination. So this guy is major. And I should write the other one as minor, just to be complete. Okay. Very good. Excellent. Let's try that question again, where substitution created a complicated scenario where I originally was stating you didn't have to draw racemic attack in SN1. Let's see if we can reproduce that and show why you would have to draw it more clearly. It shows quite nicely how these questions can quickly get complicated. What we're going to do is block off E2 attack on a large molecule. So I'm going to draw it fairly large so it's pretty easy to see. And I'm going to block off, I'll put a BR here, and I'm going to totally block off any attack and I did think I used two CH3s in the one I was looking at, which would make that center not chiral because it has two identical groups. And now I'm going to put a group here that you can't pull off. Let's just try, like, fluorine's really bad at leaving groups, so let's try CF3. CF3 is quite electronegative. Maybe I don't want to do that. I want to make it tertiary. How about an aromatic ring? That might mess us up too, but we'll try it. We'll see if this does a problem. Okay, a chair conformer with an aromatic ring. Now, I can assure you, I'd probably not give you something this complicated on the test. But it is an interesting problem. And let's hit this with a weak base this time, but a lot of heat to favor elimination. This might give us E1 this time. Okay, and just to ensure there's no E1, we will write no E1, which you would assume on a test anyways, because I have told you that we don't get E1 for alkyl halides. Well, that's not always the case, but it usually is. So I'm killing off E1 as a possible option. Can E2 occur here? Well, this carbon, this beta carbon has no hydrogens off of it. This beta carbon and this beta carbon have no antihydrogens. Heat means E2, but there's no antihydrogen, so E2 can't happen. I've shut off E1 as a possibility for this question. That leaves what can occur at this position. Well, this guy is a tertiary carbon. Bromine is a tertiary carbon. I have what was a weak base, a weak nucleophile. Even tertiary benzylics can only go, it is benzylic, can only go SN1. There's too much steric effect back here to get SN2 attack. Which means if this center is chiral, you would get a racemic mixture. All right. Is it chiral? Well, if I look at it, it has two identical groups here and here. And if I proceed out CH2, CH2, it's two identical groups and two identical groups. So this center is not chiral. Right. In that case, you'd usually say, if it's not chiral, I don't have to worry about it. I can only have to draw one product. It should give me the same thing. So let's draw the products. The Br leaves and OH goes on. And I'm going to put OH here. And for the phenyl, I'm going to just put AR for an aryl group. Okay? And then I've got my CH3 down. Now let's draw what would happen because you go through the carbocation. This would have gone trigonal planar. It's resonance stabilized by the aromatic ring, so when it shifts, it's also tertiary. You could get attacked from the other side, so let's draw the racemate, even though I said, well, it's not chiral, so it shouldn't matter. In this case, the aromatic ring's up, the OH is down, CH3 stay where they are. Oh my. If this center is not chiral, these two structures should be the same. Are they? Well, if you like, both methyls are pointing down below the ring in both structures. So both methyls are, let's call them cis or Z to each other off the ring. Who's pointing down off this carbon? On the same side the methyls are. Well, on the top one is the aromatic ring, on the bottom one is the OH. Now we've learned that due to hindered rotation, you can get EZ isomerism. And having groups pointing on the same side is different from having them point on opposite sides. What that means is these two structures are not superimposable. They're not the same. But why would that happen in this case if this center's not chiral? It occurs because these centers are chiral. Take a close look. This carbon right here has a hydrogen, a methyl, a carbon with a bromine, and a CH2. That's 4 different groups. This carbon will be the same way. It'll have 4 different groups. Because these two centers are chiral, this causes AR up and OH down to be different between these two molecules. Now, that goes beyond the scope of what I want to do in this course, but I thought it was worth pointing out. So, if you don't follow that, you can skip that point. This certainly would be a more challenging problem. If it was ever given on a final exam, it would be the type of question meant to separate out those who are really learning their stuff. And it, as I said, is very unlikely to reach a test. Let's try one more problem for E2. And that problem on E2 reaction mechanism is this molecule. So I hit this with a powerful base, apply heat. What's going to happen? Well, if I apply heat in this case, strong base favors E2. I have to look for antihydrogens. I must find my beta carbons. The bromine carbon is the alpha, and so I have a beta carbon here and a beta carbon here. The beta carbon on the left has no hydrogens off of it, so there's no antihydrogens to pull off. And so only the beta carbon on the right, the methyl, has hydrogens that can get anti and be pulled off. And because of that, the only product I get for E2 elimination would be this guy. But what if I said, let's try E1. Use water as the reagent, a weak base, hit it with lots of heat, and somehow force it to go E1. When a molecule goes E1, you form carbocations. You have to think rearrangement. You have to draw the carbocation on scrap paper. So let's do that. You have to ask yourself, what kind of carbocation do you have? And if I ask myself that question, I see the pluses on a carbon that has 2 carbons attached to it, it's secondary. Is there anything I can shift to make a more stable carbocation? Indeed, I could shift the methyl. If I shift the methyl, I get a methyl here, I get a methyl here, and I get the plus there. That carbon right here with the positive charge has 3 carbons attached to it. It is tertiary. Is tertiary more stable than secondary? Indeed it is. But it's not the most stable carbocation I can make. Why? Well, I can also, instead of doing a 1,2 methyl shift, as I did in the previous, I can do a 1,2 CH2 shift. If I do a 1,2 CH2 shift, this carbon is shifted. Which bond is shifted? Well, let's draw which bond. Let's show you which bond's actually shifting. It's this bond. This bond right here has jumped over to that position. This CH2 group has shifted from here to here. Let's put a positive charge in. What kind of carbocation did I get? Well, the carbon right here bears the positive charge. The carbocation I've gotten is tertiary. Okay, tertiary is more stable than secondary. I buy that. But why would tertiary be more stable than this tertiary? And the answer to that is that you are expanding the ring from a 5-membered ring to a 6-membered ring. 1, 2, 3, 4, 5, 6 carbons. 6 carbons reduces ring strain to a minimum. By adopting the chair conformation, you get to staggered hydrogens, perfect 109.5 degree bond angles. So you're not just getting a tertiary carbocation, you are getting a tertiary carbocation with reduced ring strain. This means more energy netted, and that means that carbocation is more stable. Now, once you form that carbocation, you have to hunt for beta hydrogens. And so, if the carbocation carbon right here is positive, then the beta carbons here, beta carbon here, and beta carbon here. We have 3 beta carbons where we can pull off hydrogens. And with those 3 beta carbons, we get 3 different alkene products, because there is an H here to pull off. And there are H's here to pull off. And there are H's over here. So, what we're going to do is pull these H's off. And one at a time draw products. And I'm going to do that now. So if I pull, for example, the H off here, I would get this alkene. If I pulled this H off, next door, off the beta hydrogen, and the 2 electrons from the bond formed a pi bond, the 2 electrons from the CH bond. Well, let's make that a little bigger ring. Then I would get the double bond forming here. And if I pulled finally the H's off the CH3, make some room here, I would get this product. Plus, plus. Okay, so what you see there are the 3 products that would form. I have to identify which is major. The more substituted double bond is major. The more substituted double bond has more carbons off of it. The double bond shown here has 4 carbons off of the double bond. This double bond has 1, 2, 3 carbons off of it. And this double bond only has 2 carbons off of the double bond. So this is clearly the major double bond according to Sayseff elimination. And this one is minor. Okay. The next example in our elimination reactions are examples of special situations, special reactions. Reactions where normal rules of Sayseff elimination and the product that you would expect to be major is not. And let's look at these 2 examples as we close our scribblecast on elimination reactions. The first case is an example where the alkene you expect to be major is not. And we have to explain why. This is the one example of Hoffman elimination that you will be required to remember. In this example, actually we can put another CH3 here. In this example, we are doing E2 elimination. E2 elimination on this alkyl halide. So we're hitting it with a powerful base, like hydroxide. We could use a bulky base, and let's, instead of using hydroxide, and it would work with hydroxide, even drive this more Hoffman-like by using a bulky base like tert-butoxide. Tert-butoxide is tert-butyl alcohol, where we've replaced the OH, we've pulled the OH off and we've made the alkoxide. This is a bulky base, so it's a very bad nucleophile, but it's a sterically hindered base. It is a very good base. It's good at grabbing protons, but it has a hard time getting at sterically hindered positions. If we look at this example, we look for our beta hydrogens. Our alpha carbon is the carbon bearing the bromine. That's this guy. There's our alpha carbon. So we have a beta carbon here, and a beta carbon here, and a beta carbon here. These two beta carbons are both methyls, and if we pull the H off either one of them, we'll get a CH2. Whether the double bond's pointing down or sideways, it'll be the same double bond. The beta carbon with the CH2 will make a different alkene, so let's draw both alkenes. Okay, if we pull the H off the CH2, we would get a double bond forming here, and when the bromine leaves, we would have two CH3s off of this carbon. If I pulled an H off one of the beta methyls, I would form the double bond forming off the end, and I would get this alkene. And you would get this alkene out to one of the formula methyl groups. Now, which one, according to Sayseff rules, is major? Well, the more substituted bond is always more stable. The more substituted bond, up here, the double bond has a butyl and two methyls, that's 3 groups. This double bond has a methyl and a neopentyl, that's 2 groups. The upper one is the more stable. There's no doubt about that. It's the more stable double bond. But is it major? In actual fact, it's minor. Why would the more stable be minor? That is, why would Hoffmann elimination take place here? Hoffmann elimination takes place because these methyls, here, 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 they are free to rotate and they block attack. The base, with its electrons, can't get at those hydrogens off this beta position. These methyls cause steric hindrance. Steric hindrance in these positions prevents the base from getting at those protons. And because they can't pull off the protons, you can't form the more stable alkene. It happens less often. Less base molecules get in there. And so the less stable alkene actually predominates due to the steric hindrance in the original alkyl halide. So this is one special reaction that you need to remember. Where, and it'll be this specific molecule, where Hoffmann elimination occurs and the less stable alkene is major. We can get another unusual situation happening when we attempt to examine the elimination product from a molecule such as this scenario. This alkyl halide, and we try to predict major minor. Now this molecule does follow Sayseff rules. Again, We find our alpha carbon and then looks for our beta carbons and beta hydrogens because we have to pull two groups off. Here's our alpha carbon, the bromine's going to leave. We have two beta carbons here and here. So we can pull an H off either of those and generate our alkene. If we do this, and again I use a powerful base and heat to indicate E2 elimination, we can get anti, the way I've drawn it. We'll get two possible alkenes. If the beta carbon on the left is deprotonated, we will get this molecule forming. If we pull the H off the beta hydrogen on the right, we will get this alkene forming. Now my question is based on stability according to the number of substituents. Just using the number of substituents, who should be more stable? Well, if I look at this double bond, it has a phenyl and an isopropyl. That's two groups. If I look at this double bond, it has two methyls and a benzyl. Well, that's three groups. He should be more stable. But in actual fact, he's not. Why? Well, it has to do, this molecule is not more stable because there's another factor that can stabilize double bonds, and that is conjugation. Remember, conjugated double bonds are double bonds that alternate between double, single, double. And we see the double bond we form up here is conjugated with the aromatic ring. What that means is if you actually look at it on an edge-on view, conjugated double bonds, the two p orbitals that form around the benzene ring, they all interact side to side. And the conjugated double bond we have over here has side-to-side interactions with the pi cloud of the aromatic ring. This leads to delocalization of electron density. Delocalized electron, I'll just write delocalize electron density. If you delocalize electrons, you stabilize them. So conjugated double bonds are more stable because of electron delocalization. The ability to delocalize electrons stabilizes conjugated double bonds, making them more stable than even, in many cases, more substituted double bonds. And so in actual fact, this is Sayseff, but he is major. So watch for conjugated double bonds. This can crop up. This can be conjugated with an aromatic ring, or we could have it conjugated with another alkene group, like this. That would be conjugated as well. So watch for that. Watch for pi bonds next door to the alkene that's forming, which gives you conjugated double bonds. They will often generate major products. Well, we have covered here a lot of elimination reactions. I hope this has been useful. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.